Good morning, Chem 101 folks, and hold on tight because we're gonna like follow the yellow brick road down the old energy problem. Anyway, today, well, at least what we talked about before was basically what energy was, state functions, things like that. And today, what we're gonna do is we're gonna dig into enthalpy, which is like heat energy, like because we were looking at work. And today we're going to look at Q, which is like enthalpy or heat energy, and we're going to look at how we measure it. Because work's pretty easy, change in volume, and it's pressure times change in volume. As long as your pressure is constant, like everything works out pretty well. You just measure the change in volume. Super duper easy. PV equals nRT. If you're dealing with the gas, you just find the number of moles that gives you your change in moles is equal to your change in volume. Super easy. But what's not super duper duper easy is finding that Q, the heat energy. But it's really similar to what we did last year with calorimetry. Q equals MC delta T and specific heat and all that. It's very similar, but again, we're going to dig into it just a little bit deeper. We're going to get a little more detailed. We're going to catch all those little things that we just sort of ignored. And that's what we're doing today. Enthalpy and calorimetry, which is basically how we measure enthalpy, like heat reaction and stuff like that. So if you're ready, even if you're not, here we go. All right, so enthalpy and the first law of thermodynamics. Let's see if I can make this thing happen here today. Nope. No guarantees. All right, so we got this here. Internal energy of your system is equal to heat energy plus work. Work we talked about last time, and this time we're going to talk about Q. So at constant pressure, atmospheric pressure, your Q, like your heat energy, is going to be delta H, right? And work is, negative pressure times the change in volume. And we call this negative because if you have a positive change in volume, if it's increasing, that means that those, like your system, your sample has to push against the molecules of the atmosphere and do work to the surroundings. Does that make sense? So if you have a positive delta V, that means work is leaving the system. That's why we're calling this right here negative. Yeah, you guys dig what I'm saying? And that right there, that's where we're going to be digging into today. All right, so Q, because Q is the same thing as delta H, I mean, that's how we find it, we can rewrite it this way. The internal energy of our sample is equal to delta H minus P delta V. Let's solve for delta H, shall we? We're just going to do some basic algebra. Boom! We're going to add P delta V to the same side, and that means delta H is our internal energy plus pressure times the change in volume. Why do we do these mathematic gymnastics? Well, it helps us solve stuff. You know what I'm saying? So here's the deal. Enthalpy, this stuff right up here, this is used to quantify heat flow. In other words, this is like what we actually use to measure the full amount. This is like the stuff that we actually measure. You dig? Let me go like that. That's a lot better. Where'd it go? Guys, this is killing me. Bam, there. Oh, look, now I'm going to underline and stuff. And hey, am I? Nope. Looks like I'm not underlining and stuff. There. Now I will be. All right. Sorry. Got all ahead of myself. Got all excited. You guys remember this from last time, right? Delta H is products minus reactants. It's like final minus initial. Delta H, as you remember from last time, it is negative if it's giving off heat. It is positive if it's absorbing heat. This is stuff, you guys remember this from last year. So if we have a solid, right, and we have to convert that into a liquid, that means that this is going to absorb heat. That means delta H has to be positive, right? It has to be positive because this is like it's like your energy bank account. Same thing with this stuff. If we have CH4 and H2O, methane gas, the energy is dropping, right? It's going to become way more stable. That means your delta H has to be negative. It's got to be negative because it's giving it off. It's getting rid of it, just like your bank account. Positive is adding, negative is getting rid of, right? Bam, there it is. Here the products are less than reactants. Here the products are more than reactants. So yeah, you guys got that stuff. That's not even hard for you. I'm not scared for that stuff. All right. I'm just burning through this stuff really quick, guys. For this, woo, there you go. We're going from a solid to a liquid. Guys, you know you have to put energy into this. Like, this is ice, and this is just like liquid water. You know you have to add heat, so like it's gonna have to be positive. Like this part is not terribly difficult for you, right? What is new and spicy is this right here, where we're going to start quantifying it. We're going to start quantifying exactly how much energy is going into or out of our sample. That's that's what it's all about, quantifying stuff. You know what I mean? Like actually putting numbers to it. So this is a silly diagram with some words and blah blah blah, and this is our chemical equation. And so this is what this equation is saying. Let me see if I can translate. This means that 1 mole of solid H2O or ice changes to 1 mole of liquid water, and in the process it's going to absorb 6.01 kilojoules per mole. Yeah, does that make sense to you guys? So this tells me that that's going to be an endothermic process. It's an endothermic, and that's how many. Oh, also I want you to be careful here. Do you see this right here? Do you see that kilo? Right. So this is actually 1, 2, 3. It's actually 6,010 regular joules. Don't let those units mess with you. Got it? Awesome. Let's move on. This is really super basic stuff for you guys. In this case, we're going from methane to carbon dioxide and water. This is going to be exothermic, right? Because it's going to be giving off. And wow, that's like a whole lot more. 890.4 kilojoules are released. How do we even know that? That's coming up next. And what does it look like in an equation? It looks just like this. So I want you to also, so we got the kilojoule part. Now for this equation, this is going to demonstrate another little detail that I want you guys to look at. 1 mole of methane combines with 2 moles of oxygen and yields 1 mole of carbon dioxide gas and 2 moles of liquid water. So what this means is if you have 1 mole, that's so bad. If you have 1 mole of CH4, you will liberate or give off 890. So it's 890.4 kilojoules per 1 mole. But that's not quite the case for oxygen, because oxygen, there are 2 moles here. Does that make sense? So if we wanted to find out how much per oxygen, what we have is kilojoules per mole, right? Well, how many moles of O2 do we have? Yeah, there's like 2 of these, right? So 2 moles will yield this, so we're actually going to have to divide it by 2. I don't know if that makes sense. So like, because it has to cut in half. Because if 1 yields 890, 2 oxygens, each one's going to be half of that, because it takes 2 to make that happen. Does that make any sense at all? Maybe a little bit. Maybe. I don't know. We'll see. We'll see. Moving on. All right. So the reason why I was talking about that is the stoichiometric coefficients in the equation always refers to the number of moles of a substance, and that's what comes into play with these, like, when you're calculating the amount of energy per mole of a substance given your equation, right? Like that. We talked about that earlier, right? If you have a solid and you're going into a liquid, you have to add 6.01 kilojoules in order to melt one mole. You guys dig what I'm saying there? So yeah, if it takes 6.01 kilojoules to melt 1 mole, right? To melt 1 mole, then how much do you think do you need to take out in order to go from a liquid to a solid, right? And now this one, you know, it's going to have to be negative because energy is going out, right? Like if we go from a liquid over to a solid. Well, it just so happens that if you reverse it, it's just the exact same thing, only like an opposite sign, right? You see that? Which is really convenient for us later on when we try to figure out how, like when we really try to like dig into delta H's of certain reactants and stuff. So forward, reverse, the delta H is the same. The only thing that changes is the sign, again, because like remember this, like the sign tells us whether it's going in or out, right? It tells us the direction of the energy. And if like, okay, so this is based on 1 mole and 1 mole, and so that's 1. Now if we take this whole thing and we multiply it by 2, we're going to distribute the 2, and we're going to distribute the 2, and guess where else we distribute the 2? 2. Right, so like if we want to double this, we're going to double everything, right? So double water, double solid water, double liquid water. That means you're going to need double the energy. Pretty basic idea, but I wanted to point that out and have that laid out so that it's not like, what are you talking about, right? It's just like anything else. It's like basically additives. It's additive. And it's also here, like it's also pretty important for us at this point to start really paying attention to these, right? We really have to pay attention to the phases of our our reactants and products, because they're different, right? So the specific heat of liquid water is much different than the specific heat of ice, and is different than the specific heat of steam. So it's going to be really important for us to start paying attention to those little bitty, details about, what phase a substance is in and whatnot. Here let's dig into why. Oh, right. See, because like going from a solid to a liquid is one phase change. From a liquid to a gas, oops, there we go, is a whole different phase change. And if you notice, this is a really rather significant difference in energy there. You guys dig what I'm saying? So you really need to pay attention to whether you have a solid or a liquid, and also it's going to be listed as different in your book. So it's just something to pick up on, so that when you go to find your like delta H's, you'll like actually have the right delta H to do your calculations and stuff. All right, let's do our first example. Super easy. Given the following thermodynamic equation, calculate the heat. So I guess that means Q. They're going to want to find Q when 87.9 grams of SO2 is converted to SO3. Okay, here's SO2. It's converted to SO3. My delta H is, it looks like it's going to be exothermic. It's minus 198 kilojoules per mole, but my problem here is I have 87.9 grams. So I guess there's a couple ways we can go about doing this. Instantly, my brain goes like this. The first thing I want to do, here, let's go like this so I can, I'm going to try to like make things clear for my brain, is step 1, I'm going to want to go from grams to moles. Right? Because what I've got here, I'm given grams. It's not, yeah, I can't, and this is moles. I got to get everything in the same units, and the units of chemistry are moles. And then once I have moles of, what am I starting with? Moles of SO2. I'm going to convert that to kilojoules. Right? So for this, I'm going to use the GFM. And for this, I'm going to use delta H. Right? So that there is my plan. I'm gonna put you guys on pause for 2 seconds. So I'm gonna go see if I can calculate this GFM, but I'm not gonna waste your time. Well, maybe I will. All right, I'm back, and look, just like that, magic. Here we go. We have 64.07 grams per mole. So for my step 1, the first thing I'm going to do is I'm going to convert grams to moles. So step 1, I've got 87.9 grams. I'm going to use the lines of pain as always, because why would I do anything else? It's going to be 64.07 grams per 1 mole. Get out your calculator, make sure I'm doing this right, because I'll probably do this wrong, and then you guys will tell me after we do this whole stupid video. All right, 87. All right, I'm getting just about 1.372. That's pretty bad. 1.372. Yeah, all right, there. All right, so for step 2, I guess, like I said, there's different ways of doing this in orders of operation, but this is just like right where my brain goes because I love using lines of pain. So if I have 1.372 moles, yeah, right, lines of pain, and it says right up here, 198.2 kilojoules per mole. And according to my, oh wait, oh no, that's going to be for 2 SO4s. See how I caught that? I just caught a mistake there. Look at that. Yeah, remember? So remember what I kind of said earlier with the H2Os? If there's 2 H2Os and you have to double, so if there's 1, then you just cut it in half. Well, this is how we're going to cut it in half using a mole-to-mole ratio. Where did I get this? I got it from here, from the equation, because this equation is telling me that 2 moles of SO2 is equivalent to 198.2 kilojoules. You dig? 2 moles per mole. Yeah, you guys get what I'm saying. So let's see if we can't math. Whoa. Let's see if we can't math that out. That's some serious mathing. So you should really double check me on this one, because yeah, you guys are gonna have me math here. I don't know if I'm right, but I'm putting this down. I hope I got that right. I don't know if I did, but there's my answer, 135.97 kilojoules. And let's get all like technical and be smart here about this. I've got 3 significant figures here. That is 3 significant figures. This measurement is 4 significant figures. So I'm gonna go like that. Aren't I like thorough and very specific and clear and stuff? All right, let's move on. All right, so delta H and internal energy. We can do this one, man. This is like an example of taking sodium, you throw it in water, and it explodes, right? And this is what's pretty good to have here is like 2 NaOH. This is a solid. This is a liquid, and if you look over here, that's aqueous. That's basically a liquid, but here, that's an important thing. That's a gas, right? So the gas is important for us because we now know that there's going to be 1 mole. Oh, that's weird. We now know that there's going to be 1 mole of gas produced, right? So there's going to be some kind of like work being done here. And we know that when this happens, right, we take 2 moles of sodium, we add it with water, it's going to release 367.5 kilojoules per mole. However, there's this weird thing. Look, this little picture down here is going to help us out. As this happens, do you see how like the hydrogen gas is being given off and it has to push out against its surroundings in order to expand, to be given off, which means that this gas is doing work on its surroundings. So what that means is with our delta H, right, with this reaction, it's not going to be like just purely like that, because this internal energy is going to drop a little bit because of the work that the gas is doing on its surroundings. Does that make sense to you guys? Well, if not, let's see if we can like explain a little bit better here. I'm going to move my face out of the way if it's at all possible. All right, so remember, the internal energy of a system is equal to delta H minus, this is P delta W, delta volume. Remember, that's work. And down here, we're realizing that this sample, it's going to have to do work on its surroundings, so it's going to lose some energy, right? So we have to figure this out. How do we... Cats. How do we figure this out, man? Well, here's how. We have conditions of 25 degrees Celsius. We have 1 mole of anything is 24.5 liters, and there's your 1 ATM. You guys get what I'm saying? So what we're going to do is we're going to add our pressure in our pressure, and we're going to add our volume into our volume, and we're going to find out what our actual internal energy is here, right? So P delta V is 1 atmosphere, 24.15 liters. So this work is going to be equal to 2.5 kilojoules. Do the math out real quick. Oh, yeah. Remember, we have atmosphere liters. And then in your book, there's a conversion. I can't. What is it? It's 101,000, 101.3 thousand. Oh, yeah. Right in the back of the book. Useful conversion factors. 1 liter atmosphere is equal to 101.325 joules. Simple conversion, lines of pain, blah, blah, blah. That's how we came up with this, that Jim John right there. So moving right along, what does this mean for us and our internal energy? The actual internal energy is going to be this. It's going to lose that, right? Because that is our delta H. We have that over here. Here, let me go like this so I can like understand why this does this sometimes. All this just so I can go. So this one reaction is going to lose 367.5 kilojoules, right? But it's going to have to lose also 2.5 kilojoules, so that means that the whole like kit and caboodle altogether is going to be minus 370 kilojoules per mole, because it's going to lose energy from the reaction, and it's going to lose energy because it had to expand and do work on the atmosphere, on its surroundings. You guys follow me with that one? So basically, anytime we have a change in volume, right? Like if we do produce a gas, our internal energy, right, is going to have to like account for the fact that we are doing work on the surroundings. All right, another example, super easy, right? They all are. All right, calculate the change in internal energy when 2 moles of carbon monoxide are converted to 2 moles of CO2 at 1 atmosphere. Well, all right. So delta U contains internal energy. What was our equation? Delta U is Q and delta H. All right, so here's my delta. Oh, I did that all wrong. Give me a second here, guys. Sorry. QW plus work. All right, so Q. Oh, this is going to be really convenient. Look, because our equation has 2 moles, and we're starting out with 2 moles, so I don't need to do any weird things like that. So I know that my delta U, so the delta H is pretty easy, is going to be minus 566.0 kilojoules per mole. And now all I got to do is figure out work. Well, this is kind of a problem here, isn't it? Because here's my pressure. I don't have any pressure. I don't have any change. I don't have any change in volume. So here, I'm kind of stuck in a bit of a pickle here because I gotta figure out some way to. I have to deal with this. This is my problem. Well, all right. I'm gonna harken back to last chapter. It's almost like this was done in order for a reason, and I have no idea why that stuff is happening. Maybe it's because I'm a lefty. I do know that PV equals nRT, right? So here, this is how I'm gonna solve the work done. PV equals nRT. All right. So the pressure is staying. So what's changing in here that's going to be changing in this? It's going to be this guy. This is the thing that's changing because I'm at 25 degrees Celsius. My pressure is that. So they're pretty much they are not the ones that are changing. This is what's going to change, right? So if I have P delta V, the thing that's causing the change in volume is the change in moles. There's my R, there's my T. So in this case, my change in moles, I have 2 here, I have 1 there, I have 3 moles here, and here I have 2. So it's going to be -1, right? My T is going to be 298. And here, I really want you guys to pay attention. I'm talking to you, Mike. Shut up and pay attention. Go do some push-ups or something, or run around in a circle real fast so you can focus in. You gotta focus in. This R, this is kind of a problem here, right? So we are used to just plopping in 0.0821, but I'm gonna use my book right quick because I don't remember anything. Liter atmosphere. So this is liter times atmospheres divided by Kelvin mole. Right? Which is great. Except this equation up here, I don't see liters, atmospheres, or anything. What I do see is I see joules and I see moles, right? So there are joules here, not liter atmospheres. So going back to the textbook, my other gas constant, which is 8.3144, now here's the key part. This is in joules per Kelvin mole. You guys see what I'm saying? So how do we choose the gas constant? Always looking at the units like around us. In this equation, we are dealing with delta U, internal energy, which is measured in joules. We're dealing with delta H, which is in joules per mole. So this one we're gonna have to use this R value. So I'm gonna pop in yeah, is that you guys follow me on this one? I hope so. So when I'm all said and done, I'm gonna be left with joules, right? Because I chose this gas constant, which is joules per Kelvin mole. This is 1 mole. This is Kelvin. The Kelvin and the mole cancel these out. I'll be left with joules, which is exactly what I want. Let's check this out. 8.314 times 298. Again, check my math because, yeah, I know. What have we got? 2477.6 joules. So I'm just going to slap that right in there, right? I'm just going to take this, I'm going to slap it right in there, and I'm going to go about my day, right? I hope you're saying wrong. I really hope you're saying wrong, because we just had this big problem with choosing my R value. Am I using this R value or am I using this R value? Man, how do you know? Because you looked at the units. Man, you're looking at units. Look, kilojoules, joules. We're gonna fix that. All right, we're gonna go back to red because we're gonna go back to our original problem of the change in internal energy is equal to negative 566.0 kilojoules per mole. And now our work. Is it doing work on the surroundings, or is the atmosphere pushing it down? We are going from 3 to 2, which means we are contracting. The atmosphere is pushing it in, so that means the surroundings are doing work on our sample. How much work? Well, let's make sure that it goes into kilojoules. 1, 2, 3. 2.4. Oh, hey, I'm wrong. This isn't per moles because we're doing it 2 to 2, and we're just going to kill that moles because it's gone. Equals, you add them together, and there's your answer. $568.5. Well, actually, 568.4775. Boy, I hope I did that one right, too. Yeah, you never know with this thing, do you? You never know. Super easy. All right, so here's what we're going to do. What we were just looking at here previously was like all of our internal energies. What is enthalpy, like delta H and all that stuff. And the next thing we need to look at is specific heat. And with specific heat, we're going to dig into calorimetry. However, we're going to take a big pause here. And what I want you to do are like the first set of questions in your text. So that's basically 622 to 628. Theories, a couple of work problems. I think that's enough for us to like take a timeout right here. We will pick it up next time with specific heat and calorimetry. So yeah, 622 to 628. I think you can handle that number of homework problems, but I want you to dig through those before we go into the specific heat, just so that things are clear in your head. All right, this was super awesome. Good time, fun. Deuces.